Welcome back, Physics 30. This is the Part C booklet on electric circuits and Kirchhoff's laws, series and parallel circuits, the last book in the electricity section that we'll be doing. Here we'll look at equivalent resistance, recognize that Kirchhoff's laws are applications of the law of conservation of energy and the law of conservation of charge. We'll state Kirchhoff's first, second law, we'll use those laws and assist in understanding the transfer of energy through series circuits. Use Kirchhoff's laws to solve problems related to electrical circuit analysis. Draw schematic diagrams of series and parallel circuits. Recognize and apply mathematical expressions for current, potential difference, and resistance in series and parallel circuits. Determine an equivalent resistance to replace two or more resistors in an electric circuit. Apply an understanding of equivalent resistance to problem solving, and recognize the importance of using Ohm's law in analyzing circuits. So we'll look at the first law here of Kirchhoff's current law for series circuit. So of course, series circuit, there's just one loop to go through, and the total current in the circuit is equivalent to the current going through any of the devices in that circuit. Okay, so they all have to be the same. And you can think of it like water flowing at the same speed through every part of a hose. So as you can see here, the electrons start at the battery, they go through this light bulb, this light bulb, this light bulb. There's no other option here. The total current generated by the battery goes through every single piece of that circuit. So if the total current is 3 amps, the current going through the first one, second bulb, and third bulb, they all must be 3 amps. Okay? What is Kirchhoff's current law for parallel circuits, though? In this case, we add the individual branches. So if it's a parallel circuit completely, it gets split off. And we can think of it as if a garden hose is split, water would split between two directions and flow at different rates depending upon the thickness of the hoses. Okay, so for splitting the current, it would in fact change. And with current, of course, we're looking at speed, coulombs per second. So if we look over at this circuit, there's actually 3 choices for the electrons to go through. They could go through our resistor 1, resistor 2, or resistor 3. So if we measure that there's one, and of course remember an ammeter measures current. If we hooked it up here, we would know how much goes through R1, R2, R3. If it's 1 amp, 2 amp, 3 amp, to figure out the total current generated by the battery, we simply add up the currents as you see over here. So it's 6 amps. Electron's energy as it leaves the battery, it passes through devices. The electrons contain energy when they leave the battery, and then they use up that energy in doing work in lighting up a light bulb or going through a resistor, etc. So we can view that as electrons get most of their energy when they leave the battery, they lose energy as they pass through devices, and they basically return to the battery with essentially 0 energy left over. All energy has been used up in doing work on the devices in the circuit. So current, we looked at that. Voltages, potential difference. For a series circuit, the total voltage is equal to the voltage going through individual ideas. And here we're looking at the total potential difference at the start is energy used up in doing work on lighting up the light bulbs or whatever the devices are. So the sum of all energy losses from the devices should equal the original energy gained by the electrons from the battery. So if they start off with this much energy, then they lose up all their energy going through the devices. So if we look at a series circuit here, if it's a 12-volt battery, and we have, let's say, 2 resistors here, resistor 1, resistor 2, or if you recall, voltmeters are hooked up in parallel because they want to measure the energy before and after, and we'll get an idea of the loss of potential, the voltage drop across each device. So if it's a total 12-volt battery, and if I measured that the voltage drop here was 8, that must mean the potential drop must be 4 here, because electrons return with essentially 0 energy. So 8 plus 4, 12. Parallel circuits, however, the total voltage is equal to each individual voltage drop, because if the whole circuit is made up of branches, once again, that whole energy must be used up. So electrons must use up all energy when they return. In parallel, electrons lose all energy in the devices that they travel through. For example, if we look at this, 12 volts, there's a choice of going through either R1 or R2. No matter which one we go through and no matter which size the resistors are, I have to use up all 12 volts when going through a resistor. So if the electrons choose this way, use up 12 volts, return to the battery. Or going this way, use up 12 volts, return to the battery. Notice here that the electrons would not come up and go up through this circuit because there are electrons coming down, and once again they want to achieve an area of low potential. So as you can see here, the laws here are kind of vice versa to what they were with the current laws. Okay, so if we take a look at that now, read over the series parallel combination sample problems on pages 67 to 68 to see how Kirchhoff's laws apply. Complete the practice questions 1 to 6 from pages 69 to 70 below over here. Now you may run out of room here, so you may want to do this on loose leaf first of all, because I don't think I left a lot of room for you to do it here. Okay, so what you can do is do those questions there. I think that the answers are in the duotang, but if you needed the final answers, you could take a look here. And once again, make sure you run through the questions and then use this part of the video as a check to see how you made out. Okay, just simply don't copy out the answers. Make sure you can do it. And if you're running into a snag, just ask me where you may have went wrong. 11. How is equivalent resistance or total resistance determined in a circuit? We look at a series circuit first of all. So far we've looked at current, we've looked at voltage. Now the last thing is resistance. In a series circuit, we add up the individual resistors to get the total resistance. So if we increase the resistance in a series circuit, we increase the resistance overall in the circuit. In a parallel circuit, though, it's relatively interesting here. If we increase resistors in parallel branches, the overall resistance actually decreases. You can think of it as if you buy a Slurpee, for example. Using one straw, it's very difficult to suck out that liquid. But if you add 2, 3, 4, or 5 straws, it gets easier. And those straws are in parallel to each other. So parallel straws decrease the resistance. Similarly in a circuit as well. Increasing resistance in parallel decreases the total or equivalent resistance in that section because we're offering more freedoms for the electron. They're getting more choices as to what path they want to take. So here, I have a coffee stir stick analogy. They offer quite a bit of resistance if you use those as straws, but if you grab like 5 coffee straws and try to suck liquid, it's a lot easier because you're offering more paths to travel through. Okay, number 13. Read over the equivalent total resistance sample problems on page 77 to 80. Complete practice problems 1 to 2 from page 82 below. The final answers on the bottom of the page so you can check. So yeah, the answers are on the duotang pages, but maybe I'll run through a couple here with you and then you can maybe do the rest. And again here, I'm kind of running short of room here. As you can see, I extended my page here. So if we take a look at the first one, I don't have it in front of me, but I think the circuit looks something like this. So a 6-volt battery and 2 parallel branches, 20 ohm, 30 ohm. So since it's parallel, this is the relationship here. 1 over R total equals 1 over 20 plus 1 over 30. So I would enter it just like that. Figure out 1 over 20, 1 over 30. Add them up. That's decimal 0.83 repeating. So that's what 1 over RT is equal to. to figure out what RT is, you can just cross multiply here, or switch places, and RT will be equal to 1 over decimal 0.083 repeating. So if I use that, 12 ohms. So you can see here, that is what the total resistance would be, or what is referred to as the equivalent resistance. Two resistors in parallel being 20 and 30, what would that be equal to if I just had one resistor? It would be 12 ohms. Okay, next question, B here. You can take a look here. I don't have the diagram in front of me, but if you wanted to take a look at these answers, you certainly can after trying it. Similarly over here, if we look over here, here we have number 2 here, a 6, 4, and a 3 ohm resistor all in parallel. So this is how you would set it up, 1 over 6, 1 over 4, and 1 over 5. Combine that all up, 0.616 repeating, interchange with RT, 1.62 ohms. So these 3 resistors in parallel are equal to one resistor that is 1.62 ohms. And then finding the potential difference and current, etc. There you have it. Okay, so if these still aren't making sense after you're practicing these questions, please be sure to ask me about it. Okay, so that'll take part of the first part of the video. The second part will continue on with the rest of the booklet. The last part of the booklet involves you doing the questions and looking at the answers, and then you should be ready for the quiz. Okay, we'll see you soon.